Hello there. I hope you're doing all right. Um, I'm going to do a couple of examples here for absolute extrema since we are not in class today. And well, I hope you enjoy. So let's get this all set up. Okay. All right. So absolute extrema. The idea is that as opposed to relative extrema that we've studied before, we're going to talk about what's highest on an entire interval. So my representation of this is that when you're in a mountain range, there are lots of different mountains of different heights, and one mountain is higher than all the other mountains typically. All right, that value we'll call our absolute maximum. So that's this point right here, the 7.979. That's the peak. And then there could be a value that's lower than all the other values. That's our absolute minimum. So we use our notation f of c bigger than or equal to f of x for absolute maximum, f of c less than or equal to f of x for absolute minimum. All right. As we will see when we do these sort of problems, we can find an absolute extrema either at our relative extrema, what we already know to find as our relative minimum and maximum values, or at an endpoint. So you can see that this particular function falls all the way down below the relative minimum. So we'll need to test both different types of points to try to figure this out. The key driver for what we're going to do with this is what's called the extreme value theorem. If f is continuous on a closed interval, then we have to have an absolute maximum and an absolute minimum on that interval. All right, so it'll occur either at an endpoint or at a critical point. Now, it's key that the function is continuous on the closed interval because, as you can see in this little picture right here, we could have some sort of discontinuity where we might expect an absolute maximum or minimum to occur, and that would be right here at x is equal to -1. All right, so the only way that this works is if the function is continuous. We'll see a couple of examples of situations where we don't even have an absolute maximum or minimum. Those functions are either not continuous or they're not being considered on a closed interval. Okay, so what I'm going to do, since you've already watched the video on this, is I'm going to run through the check your understandings. So have page 216 ready from your books, and I will go through these problems so that you're all ready to go. So find the extreme values of f of x equals x cubed minus 12x plus 1 on the interval -3 to 5. All right. So your steps are always to find the critical points of the function. So we need to take a derivative. Let's see if I can move myself out of the way here. And the derivative is 3x squared minus 12. You factor and you end up finding out that x equals -2 and x is equal to 2 are the values that make the derivative equal to 0. All right. So cue the music. All right. Hail to the chief. Here it goes. All right. Dun, 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 dun. Oh, yeah. Okay. So here's how it goes. We've got points to check. We've got our endpoints, which are -3 and 5. That's given in our interval. And we've got -2 and 2. So we've got our far left value and our far right value. And then two kind of medium values right here in between. So we've got -3 and 5 as our endpoints. -2 and 2 are our critical points. And we ask all of our candidates, because this is a candidates test, what in the world do you think about this function? So -3, we plug it in, we get 10. It thinks 10 about the function. I don't know what that means yet. All right. We asked -2, kind of a moderate candidate, maybe a little bit on the left here. All right. And we asked -2, what do you think? And -2 says 17. All right. And then we ask 2 as well, and we get -15. And then we ask the candidate on the far right. All right. The x equal to 5. What do you think? And we get 66. Okay. All right. So we put it all together and we say, all right, what is our max and what is our minimum value among all of the values that we have? So we look at the smallest, we're looking at the largest y values. So the absolute minimum is actually -15, which occurs at a critical point. You can see that's that relative minimum right there. And then the absolute maximum is at 66, which turns out to be an endpoint. All right. And then that's what we say. So the minimum is -15, the maximum is 66. The minimum and maximum are always y values. All right, question number 2, on the same page, find the extreme values of x minus cosine of x on the interval 0 to 2 pi. A little bit of a note here, if it doesn't tell you to find a relative extrema or a local extrema, then it's implied that we're going to find an absolute extrema, okay? So first of all, we find our derivative and our critical points. Our derivative is 1 plus sine of x. Where is this equal to 0? Well, on this interval 0 to 2 pi, The only point where sine of x is equal to -1 to make this whole thing equal to 0 is at 3 pi over 2. So that's the only point we need to test other than our two endpoints. So we test 0, 2 pi, and 3 pi over 2. We only get 3 candidates in this particular election. We plug in our values into our original function. Remember, we want to find out what f of x is. So I plug in 0, I plug in 3 pi over 2, and I plug in 2 pi. And we had to do a little bit of thinking here. So after we do our candidates test, we had to figure out what our lowest and what our highest values are. So 3 pi over 2, all right, when you think about that, that's like 1.5 pi. All right, so pi is somewhere around 3.1. So times 1.5 should be about 4.5. But if I do 2 pi, that's about 6.2 minus 1 gives us a 5.2. So clearly the highest value is actually the 2 pi minus 1, not the 3 pi over 2. And of course, we can see this in our picture right here. You don't always have the graph to go by. All right, so our absolute minimum is -1 at x is equal to 0, and our maximum is 2 pi minus 1 at x is equal to 2 pi. All right, example number 3. This is a little bit trickier. So find the extreme values of f of x is equal to x times e to the negative x on 0 to 3. First step, find those critical points. This one's a little bit trickier. You got to go back. Product rule didn't go away just because first semester ended. All right, so we need to do x times e to the negative x. So you can set up your nice little cross there. When you work it out, you get e to the negative x minus x e to the negative x. And remember, we want to find out where this is equal to 0. So factoring is always very helpful. Notice both of these terms have an e to the negative x. I can factor that out. And then I set each part equal to 0, and I get only one critical point, which is x is equal to 1. So x equals 1 is our critical point. 0 and 3 are our endpoints. We plug those into our function. All right, the original function, of course, and I get 0 at x is equal to 0. I get e to the negative 1, which is 1 over e, when I plug in 1 here. And I meant to write 3. So I get 3 e to the negative 3, or 3 over e cubed, when I plug in 3. So again, if you don't have a calculator, you're going to have to figure out what's going on with this. Well, the idea is that 1 over e is greater than 3 over e cubed, because when I keep on multiplying that denominator by 2 more e's, right, it's going to make it really small in comparison to multiplying the numerator by 3. All right, so the 1 over e is going to end up being the largest value here. So our absolute minimum is 1 over e, which occurs at x is equal to 1. And then our absolute maximum, other way around. Absolute maximum is 1 over e at x is equal to 1, and absolute minimum is 0 at x is equal to 0. Sorry, I switched those two. All right, last one. What do you do if you have an infinite interval or infinity is involved in your interval? In those cases, you don't have values to actually test. So what we're going to do is we're going to use limits instead. And our limits will tell you what's going on with either the end behavior or maybe some asymptotes that are going on with our function. So find the extreme values of f of x is equal to 2x to the fourth minus 4x squared on the infinite interval negative infinity to infinity. All right, so when I do the limit as x goes to negative infinity, that's kind of like the far left limit. If we remember our pre-calculus algebra, we know that this function goes to positive infinity on the left. And indeed, if we do the limit as x goes to infinity on the right, we also get positive infinity. That's going to tell us something. So let's also find our critical points. When I take our derivative, I get 8x cubed minus 8x. Factor, and I find out our critical points are -1, 0, and 1. When I plug both of those into our function, I get -2 at both x equals -1 and x is equal to +1, and I get x equals 0, or y equals 0 when x is equal to 0. And you can see on our graph what's going on here. So what do you think is going to happen here? Do we have any absolute minimum values or absolute maximum values? And the answer is we have an absolute minimum at x is equal to -2, right? The function doesn't ever go any lower than those values, but no absolute maximum because this function continues to increase all the way to infinity. Okay. Oops, sorry about that. All right, now to our examples, page 217. All right, so example number 1, we want to find the extreme values of f of x is equal to x to the fifth minus 20x squared on the interval -1 to 3. So I've drawn the graph. You can probably tell what's going on here, but you won't have the graph. I'm just using that as an additional thing for us. All right, so in this case, we need to, again, find our critical points. We take a derivative. We get 5x to the fourth minus 40x. factor, set equal to 0. When we do that, we get x equals 0 and x is equal to 2 as our critical points. All right, so I get 0 and 2 as our critical points, endpoints -1 and 3. Just as before, we do our candidates test. We're testing to see what these candidates think about this particular function. All right, I will spare you all the I plugged in blah, blah, blah. You can see the values right here. And we can find that we've got an absolute minimum at x is equal to -48 of -48 at x is equal to 2 and an absolute maximum of 63 at x is equal to 3. And that corresponds to what we see from our graph. Even though the endpoint looks like a small value here at x is equal to -1, not quite as small as the relative minimum we have here. Okay, and just a little reminder, if I'm going too fast, just you can pause the video. They're all right here, but you do need to make sure you got your notes ready for the note check. All right, example number 2. This one's a little bit different. We've got f of x is equal to x plus 4 over x on the interval 0 to 6. Notice it's not a closed interval. If it's not a closed interval, unlike number 1, we're not assured of having an absolute minimum and an absolute maximum value. All right. What could happen is you can have some sort of a open circle at 0 or an open circle at 6, or maybe something else is going on. All right. So we're not assured necessarily of having an absolute max or minimum. And in fact, well, what do? We take a derivative. When you take a derivative, all right, one way to rewrite this function is x plus 4x to the -1. And we find our derivative, when we do that, is 1 minus 4 over x squared, which we're going to set equal to 0. So x is equal to 2 and -2 are both critical points because they're going to be values that make this derivative equal to 0. But then also x is equal to 0 is a critical point because it's going to cause our denominator to be equal to 0. So remember that from before. Critical points are not only points where derivative is 0, but also undefined. Now, we got a little bit of a problem, though, because we got an open interval. And so what do we actually test? We can't plug in 0. We can't plug in 6. They're not on the interval. But what we can do is we can do a limit a little to the right of 0, since this is the far left endpoint, and a little limit a little bit to the left of 6. All right. When we do so, if I plug in 0, you notice I got a problem with my original function here. And this function actually goes to infinity as we go to the right of 0. One way you could do that is to test a value like 0.1. So I get a 0.1 plus 4 over 0.1. And as those x values get closer and closer to 0, this part right here, the 4 over x, is going to blow up. It's going to be really, really large value. Okay. Similarly, if I test a little bit to the left of 6, all right, and I plug in, I get 6 plus 4/6, which ends up being 20 over 3. All right, so we got a little bit of an issue here. Because it's not a closed interval, we can see that we've got an absolute minimum, at x is equal to 2. That's our critical point. I notice I didn't even have to test -2 because that's not even on the interval. So there's only one value that I needed to worry about. Okay, and there's no absolute maximum on this interval because this function goes all the way up to infinity to the left, or to the right of 0. Right, so there's no absolute maximum at all. This doesn't violate our extreme value theorem because we're not dealing with a closed interval. And then we can have situations where we might have an asymptote. All right, example 3, what do we do with absolute values? So we want to find the extreme values of f of x is equal to absolute value of x minus 2 on the interval -3 to 5. We've done so much with absolute value. I hope you remember the way that we treat absolute value because we've done this so much at this point. So we find out where our vertex is, which is when the input's equal to 0. That's at x is equal to 2. You can see that from our graph. That's where the vertex is. This is a shifted absolute value function over 2 units. So I'm going to write this as a piecewise function, x minus 2 is the piece when x is bigger than or equal to 2. And negative x minus 2 is the piece when x is less than 2. That's the point where f of x is equal to 0, x equals 2. So when I take my derivative, let me fix this really quick. Okay. So when I take my derivative is 1 to the right side of 2 and -1 to the left side of 2. Well, what does that tell us? Well, is the derivative ever equal to 0? No, not quite. But there is actually a critical point. And the critical point is x is equal to 2 because to the right of 2, the derivative is 1, and to the left of 2, the derivative is -1. Since those don't match, we have a corner, right? Slopes are finite. They're not equal to each other. So the derivative does not exist at that point. That's a critical point we need to test. X is equal to 2. In addition, we got the critical points of -3 and of 5. So I plug all those in, do my candidates test, and I find my absolute minimum is 0 at x is equal to 2, and our maximum is 5 at x is equal to -3. And we can see that from our graph. So don't forget about situations where the derivative might not exist, such as corners or vertical tangents, cusps, all those sort of situations. So we need to make sure that we test all those. All right, example 4, find the extreme values of f of x is equal to x to the 5th on the interval -infinity to infinity. Again, what do we do if we got -infinity to infinity? Well, we need to use those as endpoints, in quotes, right? They're not really endpoints, but we're testing them using limits. And if you remember what the x to the 5th function looks like, it is an odd positive function. All right, so in this case, if we do the limit as x goes to -infinity, we get -infinity. And then we do the limit as x goes to infinity, we get positive infinity. Now, just for the sake of making sure we got everything accounted for, let's take a derivative and find our critical points. So when we take a derivative, we get 5x to the 4th, which we set equal to 0. So x equals 0 is the only critical point. However, it doesn't matter because when I plug in 0, I'm going to get 0, but both of my limits here, one's -infinity, one's positive infinity. So what happens is there's no absolute minimum and no absolute maximum. How does that not violate the extreme value theorem? Well, again, we're not continuous on a closed interval here, so anything's possible. We could have an absolute maximum, we could have an absolute minimum, we could have neither. All right, the last example I'm going to do is on page 218. And it says, suppose a particle moves along the y-axis with a position given by 4t cubed minus 15t squared plus 12t. What is the highest and lowest position of the particle on the interval 0 to 3? All right, so when we see highest and lowest, those are keywords for finding an absolute extrema. What's the biggest? What's the smallest value? What's the highest? What's the lowest value? All right, so we want to find the absolute maximum and minimum value of the position function on the interval 0 to 3. So just as always, same sort of problem, we're going to find the critical points. So take a derivative, we got 12t squared minus 30t plus 12. I can take out a 2 right here and end up with a 2 times 6t squared minus 15t plus 6. And we need to figure out how to factor this right here. I'll save us a little bit of trouble in class. We would have gone through all this, but this becomes 2 times 2t minus 1 times 3t minus 6. So we needed two numbers to multiply to get to 6 and add to -15 when we split it up as a 2t and a 3t in this case. So in other words, t equals 1/2 and t equals 2 are the two critical points. We've got our endpoints of 0 and 3. We plug in 0, we plug in 1/2, we plug in 2, and we plug in 3. And we see which one gives us our highest and lowest values. So as you can see, the absolute minimum value, which would be our lowest position, would be at time 2. That minimum value is -4. And the absolute maximum value, which would be our highest value position of our function, that would be at 9 and time equal to 3. Last part here, part B, same function. The particle has a position 4t cubed minus 5t squared plus 12t. What's the maximum velocity? So what is it that you think you do when you find maximum velocity? Well, you need to find the maximum of the velocity function, right? So we actually need to find velocity. Critical points will be helpful as well. So v of t is equal to 12t squared minus 30t plus 12. Derivative of that, in order to find our critical points, is 24t minus 30, which is equal to 0 at 30 over 24, or 1.25. All right, so we use that as our critical point. 0 and 3 are still our endpoints, and we're testing velocity. We want our maximum velocity value. When we plug in 0, 1.25, and 3, we got our maximum velocity, which is 30 at time equal to 3. And this is the graph of the velocity function here, not the position, but velocity. All right, so the other problems are a little bit tricky. I think this is a good stopping point for us on this video here. So remember, I've got office hours. Please let me know if you have any questions, and we'll see you when we see you.